In this interesting active circuit that is designed using 3 ideal op-amps, number 1, 2, and 3, we want to show that the input impedance Zin, as observed through this port, is effectively a negative inductance with a value that is just negative R1 squared times C, in which R1 is the value of this resistor and C is just this cap. So effectively, we are not only converting a capacitance via this circuit, simple circuit, to an inductance, but also it's a negative inductance. Let's see how this is possible. Okay, so as usual, when we want to find Zin, the fastest way is applied a test input voltage. So I'm going to apply a V test here. Effectively, what I'm doing is, let me remove this part. So effectively what I'm doing is, to find Zin, I am going to apply a test voltage like this with a value V at input. By that voltage I mean it can be a AC sinusoidal test. It doesn't matter. I'm just applying V with this polarity between that input terminal and ground. And I want to find I in that is going into the circuit. And then after I find that VI, let's say, I know that input impedance of interest is just V divided by I. So the question is, what is this I? Okay, so we know that assuming op-amps are properly biased, meaning that supply voltages are properly connected, and because of the dominant negative feedback, all op-amps are in linear region of operation, not saturated. We know that virtual short is valid for all op-amps. And then as a result of that, positive input terminal of each op-amp has the same voltage as negative input terminal. Okay, so if you apply V at this node, then that should be also here, which means this node is V volt. Okay, and this current I that is coming in, it cannot go through the input terminal of op-amp, because as long as it is linearly operating, input terminal has infinite impedance, and therefore no current can get through it. This whole current has to go through R1 and has to go this way. So that's the current I. Now, there is a current I2 that is going this way. So I need to find that current. And again, for the same argument, there is no current that can go through input terminal of ideal op-amp in linear region. So therefore that I2, and the same thing here, no current can go this way. So that I2 that I'm interested to find is the sum of, due to KCL at this node, is the sum of, so let's name this node as node X. So for node X, we know that V of node X equal to V volt input because of the virtual short that I just talked about. Now I know this current I2 is because of KCL is the sum of this I3 and this I4. So I need to find I3 and I4. That's it. Okay. Take a look at the situation that we have for the op-amp number 2. You have, as you can see, you have V volt at positive input terminal. Because op-amp number 2 is properly biased in linear region, virtual short enforces that voltage V appears at negative terminal as well. Now, there is a current that is flowing this way, and since we have a plus minus V volt drop across R3 here, and that's the same current going through this two R3 resistors, that current, that voltage drop should be here as well. So therefore V plus V here is 2V. I mean, that's obvious because this is effectively a non-inverting amplifier, and the gain of that, because of the value of resistors, is 2, and that's why from V we get to 2V, but I just intuitively also justified it. So this node is 2V. Very interesting, because this node is V, node X, this node is V, and the other side of this resistor R1 is 2V. So therefore I can say so let me just write it, KCL at node X indicate that the current of interest I2, I mean this current, is equal to the sum of I3 plus I4. Keep that as equation 1. Now, for this resistor, I can say I3 is the voltage across that resistor. Look at the direction of I3. So it would be 2V on the right side minus V on the left side divided by R1. So it's V over R1. Okay, that's I3. That's equation number 2. Okay, let's look at I4. So what's going on? Well, let me change the color so that it's easier to be seen. This whole setup here is like an inverting amplification scenario. If you look at it carefully, what you see is effectively you see that we have 2V and we have 2R2, and then we have a connection to negative terminal of an op-amp here, and then we have a feedback cap from output of that op-amp to negative terminal. Of course, you could argue that its impedance is 1 over CS in, let's say, S-domain analysis. And then positive terminal is connected to AC ground or whatever ground that we have. So as a result, this is an inverting amplifier scenario. And for inverting amplification, we know that the voltage at the output for this guy is simply input voltage. So let's say if I name this node as node Y, this node, then Vy is the voltage of interest, and I can say Vy is minus the impedance in the feedback loop. It's a inverting scenario or amplification, so it's 1 over CS divided by 2R2 times input voltage 2V. So 2 cancel out with 2. As a result, I get V, negative V over R2CS. Okay, great. So I found Vy related to V and R2CS. What's the benefit? I can find I4 now. I can nicely find I4 because now I can say I4 is just Vy minus Vx divided by value of resistor R1. So therefore I can just easily substitute. For Vy, I can substitute this value I found, which is negative V divided by R2C, negative V divided by R2CS. And for Vx, I know it's just V divided by R1. So as a result, I can say I4 in summary is just negative V over R1 times 1 plus 1 over R2CS. Keep this as equation number 3. Okay, so now I found I4, I already found I3, and I'm going to use equation 2 and 3 and substitute them in equation 1. So using equation 1 and 2 and 3, I'm going to say I2 is equal to, let me change the color so that I have a better contrast. So now I'm going to substitute for I3 and I4 in equation 1 from 2 and 3. So I get V over R1 minus V over R1 from equation number 3, 1 plus 1 over R2 CS. Okay, let's factor out V over R1. So I get 1 minus 1 minus 1 over R2 CS. Nice. These two 1 cancel out each other, and I get a simple outcome, which is V over minus V over R1 R2 CS. That is I2. So we found I2. So what is the benefit of this? the last step, this is a shortcut method effectively overall, but think about it this way, that as our last step, the voltage drop across R1 here on top should be the same voltage drop across R2 here, because on one side, both of them have voltage V on one side of resistors R1 and R2. They have voltage V. On the other side, they have a common node. So therefore, the voltage drop across these two resistors R2 and R1 should be the same. And as a result of that, I can say V of R1 should be equal to V of R2, and which then I'm going to just for V of R1 say it's R1 times the current I that I want to find should be equal to V of R2 is of course R2 times the current I2 that is going through R2. But now the nice thing is from equation 4, I already found I2. So I'm going to use equation 4 and say R1I equal to minus, so I'm substituting for I2 here. So minus V over R1, R2, R1, R2 CS times R2. Very nice, because as a consequence of this, R2 cancel out R2, and what I get is V over I. So V over I is equal to minus R1 squared times CS. And we know that V over I is basically just Zn. So let me use a different color so that we have good contrast here as well. So is equal to Zn. And we are done. So this part you see here is our L, because let me highlight the other one. This is S for the impedance Zn, and it's like an L times S. So effectively as if Zn represents or resembles an let's say resembles a negative inductance. With a value that is negative R1 squared times C. Therefore, using value of C and using value of R1, we can adjust the resulting inductance in this negative inductance in this circuit. I hope that this is helpful.